In this video, we're going to look at the impact of our optimum values W and K if we could increase our budget by a little bit. And by a little bit, we're going to consider $1 here. We're going to start with our optimization function, which was how much we can produce based on the number of workers and the number of units of capital. And we also had the constraint before that each worker cost $10 and each unit of capital cost $20. And we had a budget of $3,200. What we did before is we used Lagrange multipliers, and that led to the constraint that we had 3K over W is equal to 1/2, and we could rewrite that as K is equal to 1/6 of W. We found that in an earlier calculation at the optimum. That led to the number of workers being 240. When we tied it in with the constraint, the units of capital were 40, and altogether that gave us a Q value, plugging those into the formula up here, of 920.078. So we were able to produce 920 units, 0.078. That's a recap of the earlier work. Now we want to investigate the possibility of increasing our budget by $1. So changing this to 3201. There's two ways we can handle that. One is to recap all our calculations again, and the other is to look at our interpretation of lambda as representing the change in the function over the change in G, while our change in G here is the same as our change in budget. If our change in budget is $1, then somehow, if our change in G is our change in budget, then our lambda should also capture the impact of the $1 change. What we're going to see is that one of these methods is a lot more complicated than the other, and the lambda value turns out to be a very simple way to get to that same result. Let's take a look at the 3201 budget. If we had that, we can use this constraint here, simplified to K equals 1/6W, put that into our budget, which we usually called equation 3, and that gives us 10 W's plus 20/6 W's equals 3201 under the new budget. Multiplying through by 6, we get 60W plus 20W equals 19,206. And solving for W gives us almost the same as before, 240, but with a little bit incremental increase because we have a little more money to spend. With that, we also get our capital amount, which is 1/6 of that. And that's, again, almost the 40 we had before up here, but with a little bit extra. And with that, we get a prediction of the quantity we could produce, which is equal to 6 times these values here. I won't write all those out, but it's using these values in the quantity formula, and that's going to give us 920 point, this time, 0.3656. So we've seen a little increase in the productivity, and we can actually estimate that. The change in production is going to be that minus that, or 0.287 units. So a small increase in the budget, only $1, has a small impact on the quantity produced, but we can predict what that is going to be. I want to compare that, though, with the method of computing the lambda value. The lambda value can be computed from any of the equations involving the Lagrange multiplier. Just to recap these, we'll go back a few pages. So maybe pause here for a moment and while I flip the pages and find it. Here we go. Like in this equation here, the lambda value is what we're interested in, but now we know W and K from the earlier 240 and 60. We're going to copy those over and then solve for lambda this time. So using the lambda value, the idea being we already had our solution at 240 and 40, we can plug in and find that lambda is equal to 1/10 6 times 3/4 workers 240 to the negative 1/4 and the number of capital units to the power 1/4. That gives us a value of 0.28, wait for it, 7. Those two values, not coincidentally, are very close to the same. This is capturing the idea that an increase in the budget, which is our change in the constraint value, can be captured by this lambda value. Once we know that its number is 0.287, we can look at that immediately and say, oh, if I had $1 more in my budget, I could get 0.28 more units, and it's a scaling factor. If I had $10 in my budget, I could get 10 times this change in my quantity produced. And that turns out to be a lot simpler than going back to the calculations and actually recomputing the best worker and capital distribution with a slightly tweaked budget. This is a bit of a hassle. We have to go through a lot of calculations. This part, we just look at the lambda value and we can interpret that immediately, which is a very powerful tool. So this lambda value in the Lagrange multiplier equations definitely does have an interpretation, and in applications, especially ones with economic implications, that lambda has a real meaning that's easy to interpret. To round this example out, let's take a look at a graphical perspective on it now. We have our constraint, which is that our budget, 10 times the workers plus 20 times the capital, has to add up to $3,200. And notice that forms a straight line if this is our W versus K graph. So what we could do here is measure the quantity produced, which is the number on the contours. We can see as we get larger and larger numbers of workers and capital, we get more and more production, highest level up here around 2,000. But because our budget keeps us down here, all we can do is maybe produce 200 or 400 or 600, or we can see there's a sweet spot. I can produce 800 here or 800 here. Somewhere in the middle should be the best balance of workers and capital to maximize our production based on our formula for production. Well, how do we find that sweet spot? We use Lagrange multipliers to identify it, and here's a zoomed in version. The location that we found was at 240 for the workers and at 40 for the capital. And we can see at that point, we're just touching the 920 production value. It's a hair above that in practice, but we're actually able to produce 920 units versus less optimal allocations for our process. What we just did with the lambda value calculations was ask, what if we move that line over a hair? Our budget, if we changed it from 3,200 to 3,201, would just move the intercept up a bit and give us a new line. That's what we see here zoomed in on this same basic graph, but much more detailed. What we see is a change in the budget of $1 that moves our constraint over one step. So in other words, instead of spending $3,200, we can spend $3,201. We can choose between those values. And what you see is our constraint. Let's go back. And what you can see is the change in production. We were able to produce 920 before. We're now able to produce almost 920.5. So we see a change in the quantity produced of around, let's say, 0.3 on this graph. Oh wait, what did we find in our last value here? The lambda value in our calculations came out to about 0.3, representing the change in quantity over the change in our budget. And that was perfectly represented by our lambda value. So we can see how change in constraint puts us onto a new line here. We can travel on different points, but the lambda value allows us to predict in advance how big a change in quantity we can expect from that improvement, from that extra freedom. And that ties in all the elements we've seen up till now about the gradients, Lagrange multipliers, and the interpretation of that multiplier value.